Hello and welcome to Eng Phys 2P04 Lecture 21, Torsional Stress and Strain. Torsional stress and strain are responses to torques. If you try and apply a torque to an object, it's going to twist. So we are going to define the torsional strain as the change in rotation angle per unit length. Here the rotation angle is around, say, the z-axis, and the length is the length in the z-axis. It's directly proportional to applied torque as long as we're within the elastic limit. So now torque is capital T. That's because we're using tau for shear stress, so we got to have a new symbol for torque. And G is the shear modulus, as usual. Not surprisingly, this has to do with kind of shear of an object because that's what's going on as we're moving it. To be able to, if object planes can slide freely relative to each other, then there's no resistance to torsion either. JT is something called the torsion constant. This is a geometry property. It doesn't depend on the material constants, on the stiffness of the material. It's just dependent on the cross-sectional features. So if the cross-section is a circle, then this integral is pretty easy to evaluate. If the cross-section is a square, then it's a bit more complicated. We're going to say that it's approximately equal to the second moment of area. Really, it's a little bit different as soon as you start twisting the object and getting into big torsional strains, because then the cross-sectional shape changes. So if you want to get a really accurate result, then you're going to have to use finite element methods. For this course, we're not going to be concerned with doing that for the time being. All we're going to be doing is analyzing this analytically. Do we need to do anything different if we wanted to do this in FlexPDE? Nope. Actually, the equations that we evaluated, that we set up last time for general elasticity, will work just fine if you are able to apply a torsional stress to it. So this lecture is all about calculating what torsional stresses and strains we'd get analytically. The maximum shear stress occurs at the outer surface. So the angle of rotation, you could say, is the same all the way throughout the cross-section, but the shear stress is 0 at the center and gets larger as you move farther away from that central axis, linearly with R. The maximum shear stress tau occurring at the outer surface as long as the thing is in pure torsion. If there's some other loading on the system, then we'd have to examine the shear stress in combination with all of the other axial loading conditions that we've got. So just to compare the elasticity that we've got so far, we've had normal axial elasticity where stress is perpendicular force per area, strain is change in length per unit length, and Hooke's law said that they are related through the Young's modulus. In shear, we had that its parallel force per unit area is the stress. The strain, or engineering shear strain here, is the sum of the change in x per unit y and change in y per unit x. And Hooke's law is that the shear stress is equal to the shear modulus times the shear strain. Now in torsion, the torsional stress, you could say, is the torque divided by the second moment of area. The strain is the change in angle per unit length. So now stress and strain don't have units of pascals and unitless. They're in per meter, and consequently the shear stress, or torsional stress rather, ends up being in pascals per meter. Hooke's law says that the torsional stress is equal to a constant times the torsional strain, except that unlike before, where we needed a different constant for shear rather than elongation, for torsion, as long as we define things like this, then it's actually just the shear constant again, shear modulus again. We're just going to do one torsion example. This is a kind of complicated example. There's a lot in it, but it's not really anything that we don't have up here or that you could figure out with enough thinking about it. So what's going on is we've got a fixed support over here. We've got a shaft, 30 millimeter diameter, and it's made of steel with a shear modulus of 80 gigapascals. And it's connected by this gear, 120 millimeter radius. So this is, did I say radius? This is 30 millimeter diameter, this shaft. And then this gear has a 40 millimeter radius. So these gears are connected, and that gear is connected to this shaft, which has the same diameter as the shaft over here, as shaft FD. So CA has the same diameter as shaft FD, and then we're applying a torque here. The bearings at A, B, and G don't resist any kind of rotation. So if you figure that we apply a torque here and we apply a torque here, then there's going to be some twisting that goes on. So just from this torque, we'd expect the gear is going to rotate a bit, and that's going to make this gear rotate the opposite direction and place a twist in this shaft. So we're going to have a twist in this shaft, and we're going to have another twist in this shaft. So the twisting angles per unit length are governed by our torsion elasticity results, and the gears will map the torques from one gear to the torque from another gear based on the radius ratio. So if we step up the radius going from gear C to gear D, then the torque gets stepped up by the same ratio, and the rotation angle gets stepped down by the same ratio. Okay, give it a shot. All right, well, just like before with axial force and shear force internally, we can look at the static equilibrium of every section and say that, in here we've got a constant torque applied on one face relative to the faces beside it. So if we were to split the shaft in anywhere in this section, then the torque inside is the same. The torque can only change when we've got these applied torques externally. So we've got this applied torque, so the torque between A and let's call this point A prime is going to be 0. Then we've got a torque of 12 Newton meters all the way up this shaft. Then we step up by a ratio of 4. So we've got 36 Newton meters, except it's in the opposite direction because this gear rotating this way makes this gear rotate this way. So 36 Newton meters over here, and then we subtract it by 4 because that's the opposite direction, so 32 Newton meters in this direction. Let's call the direction that the torques are applied the positive, so that means that we've got negative 36 here and negative 32 over here. We can calculate so that's those numbers, that's just the torques. We can calculate the torsion constant for a circular cross-section just by taking this integral, and you find that it's pi r to the 4 over 2. So the max shear stress is r torque over the torsion constant. Substituting in the numbers that we've got, remembering that they told us the diameter of those shafts was 30 millimeters, so the radius is 15. We come up with the maximum shear stress for all of the different sections. And now how do we figure out the angle? We're going to take the torque and we're going to divide it by the torsion constant, and we're going to divide it by the shear modulus, and we're going to multiply it by the length of each section to find out the twist angle. So the twist angle here is 0. Then we know the torque in this region, torque in this region, torque in this region, and so we'll figure out the angle rotation of E by multiplying those things out, and then the new change in the angle from E to D is going to be, if we take that change in angle for here and we add it to the angle there, then we'll get the total angle of D. And because the torques are actually 32 Newton meters in the negative direction and then 36 Newton meters in the negative direction here, this gear rotates in the negative direction, in the direction that I'm showing here, which makes this gear rotate in the positive direction by 3 times as much. The gear ratio working in our favor there, or at least as long as we want more rotation anyway. Then what's going on so we take that angle that we find, so the angle of E from this change in angle, and then add that to this change in angle to get the angle of D, and then multiply that by 3 to get the angle of C, but in the opposite direction now, and then multiply that, add that to the angle change from C to this point A prime to find the total angle change. So doing all of that, first angle of E, then angle of D, angle change of C is -3 times the angle change of D, and angle change of A is the angle of A prime, because there is no torque applied in this section here from A prime to A. And we find that we get this final angle change where that's in radians. So pretty small angle change from the torques that we applied here.